Hi, it's Kiffin Lebates here, the CTO of Artema, and today I thought it would be fun to talk about a new quantum resistant signature method that we've invented here at Artema that solves the problems faced by using ECDSA or other non-quantum secure digital signatures. The community is fortunately starting to wake up to the fact that quantum computing poses a real threat to blockchain in the not too distant future, and all sorts of solutions are being proposed. The problem that most of these solutions have is that they are relying on quantum secure signatures that are huge compared to the standard elliptic curve signatures that we currently use. And this is a problem for blockchain because we've got a space problem in blockchain. The blocks have a limited size, there's only so many transactions you can fit into them, and you pay by the byte for your transactions. And so if your transaction suddenly becomes 100 times bigger because you're now using signatures that are hugely bigger, then how is that going to impact the cost of transactions, and what happens to chain sizes, for example, or throughput on the nodes? Again, quantum resistant signatures tend to be computationally intensive as well. In fact, usually there's a sort of trade-off between size and computation. So all round, it's a problem. The signature scheme that we've come up with at Artema uses cryptographic hash functions, and these are quantum resistant. They can be attacked using something called Grover's algorithm, but it doesn't really give you enough of an advantage to be able to crack them in any kind of sensible time. And in fact, one of the earliest quantum secure signatures was the Lamport signature scheme. Unfortunately, it produces signatures that are somewhere between 16K or beyond, which is vastly bigger than the elliptic curve signatures. Our method uses a commit transaction with a cryptographic hash function, and then a reveal transaction a short time later to authorize an action on a smart contract, for example, to move a token. It would work for Bitcoin as well, to authorize a transfer of Bitcoins through a unspent transaction output. It does, as I say, involve two steps, the commit transaction and the reveal transaction, but the rate at which Ethereum virtual machine compatible blockchains functions means that the fact that there are two transactions is not a problem. And the neat thing about it is that not only is it quantum secure, but the size of those two transactions together is only about 25 to 50% bigger than a standard Ethereum transaction for transferring something like Ether. And if you're making a function call or something like that, then it comes out at approximately the same size as a single digitally signed transaction. So I think that it's useful in an awful lot of cases. It's not going to be perfect if you want an immediate action to be taken, but there are plenty of two-step activities that take place on Ethereum already. For example, when you provide an approval to someone to move a token and then they move that token, that's a two-step transaction as well. And so for these kind of things, and indeed for the majority, I'd say 90-95% of transactions out there, our two-step commit reveal quantum secure transaction is perfect for undertaking standard blockchain activities. And as I said, we're looking at something that is of the same magnitude as a standard non-quantum secure Ethereum transaction. So it solves the problem of quantum computing attacking signatures and therefore breaking the security of the blockchain, and it does so in a very space efficient manner. And that's why I'm particularly excited about this invention. We've examined all sorts of cases around it as well to expand out, making the functionality much more useful. And I even have a functioning prototype working with a smart contract wallet, one of these account abstraction systems that Ethereum is encouraging us all to move to at some point in the future. So that's just a chat about Artema's quantum defense patent and our new signature scheme. I hope you found it interesting. Feel free to ask any questions in the comments if you want some clarifications on anything I've mentioned in this video. And I look forward to seeing you in the next video soon. Bye for now.